So, greetings, students. So, in this lecture, measuring instruments. Okay, so we'll be dealing with your electrical measurements and then your measuring instruments used for measuring your electrical quantities. Okay, so this is what this unit covers. So, the contents of the first two lectures will be such that in the first lecture will be dealing up to your essential requirement of the indicating instruments. Okay, so the next phase will be dealing with your types of the instruments. Okay, so the essential requirement of the indicating instruments, what we'll be seeing is that the minimum requirement for measuring any of your electrical quantity, how you can measure any of your electrical quantity, that we will be seeing with respect to your indicating instruments. Okay, so this comprises of the following, starting with your deflecting torque, followed by the controlling torque. This controlling torque is again can be classified into two types, starting with your spring control and your gravity control. Okay, so the third type of torque which we have to consider for as an essential requirement is that your damping torque or your restoring torque. Okay, so this deflecting torque is the minimum torque which is required for the deflecting of your pointer. Okay, that is you can take as a starting point, starting force which is required to move the pointer. Okay, so after that the controlling torque is the torque which moves this pointer to the particular value. Okay, you can take this as a point. Okay, so from your first position to the second position, if you want to move means, so you need some kind of force or the torque. Okay, that torque is provided under your controlling torque. So after reaching that position A, it should not move after the point A. Okay, it has to be restricted up to the point A, and this can be achieved by your damping torque. Okay, so these are the three major tasks which you have to consider for as a main essential for your indicating instruments. Okay. So in the second half, we will be dealing with your moving iron instruments. That is the different types of instruments we will be seeing. Basically, we will be seeing about a moving iron instrument, then moving coil instruments we will be seeing. Okay. So we'll be getting into it. The essential requirement. So the essential requirement, as I said, is starts with your deflecting torque, controlling torque, and it ends out with your damping or your restoring torque. Okay. So deflecting torque, as I said previously, with the deflecting torque, the deflecting torque causes the moving system and the pointer of the instrument to move from its zero position. So if the position is this is a meter scale means if it's the if this is the pointer means from the initial point A, it starts to move. Okay, so for that you need a torque. That torque is provided by your deflecting torque. So the production of deflecting torque depends upon the type of the indicating instrument. So totally there will be three types of indicating instrument that here they have given. First is your moving iron instrument. Second is your permanent or the moving coil instruments, and third one is your electrodynamic instrument. So based upon the type of the instrument used, okay, the deflecting torque will be generated. So coming to the controlling torque, okay, controlling torque if you're coming out means the pointer will be moving from a position A, so it has to reach the position B. So from the point of A, here what they are doing is limits the movement of the pointer and ensures the magnitude of the deflection. So this is the important point you have to consider. So magnitude of the deflection refers to nothing but the point at which from the initial position to the movement of your end position. Okay, so the pointer has to cover from here to your B position, that is from A position to B position, and this coverage area is controlled by your controlling torque. Okay, it is always same for a given value of the electrical quantity to be measured. So this controlling torque is generally of two types, starting with a spring control method. So you can move that pointer by your spring control or by the gravity control method. So coming to the spring control, this is how it looks like. So this consists of two phosphor bronze hairsprings. So this is a hairspring. Okay, this refers to one hairspring, and this refers to another hairspring. Okay, these will be attached to a spindle. So this is what your spindle. So this is what your spindle of the moving system of the instrument. They these two springs are these two control springs will be wound such that they will be in the opposite direction of each other. So it is clearly evident from your figure itself. So the pointer is attached to the spindle of the moving system. So this is the spindle. So within the spindle, the pointer will be attached. So this is the pointer, and this is your calibrated scale. So and the pointer other end will be balanced by your balanced weight. Okay. So this is the basic structure of your spring control. And coming to the working, how it works when the moving system deflected. So moving system deflected, one spring gets wounded. So one spring gets wounded and the other one gets unwounded. So at initial point, that is, it will be crossing your deflecting torque. So after the deflecting torque, the be some movement. So at that time of the movement, what happens is that one spring will be contracting and another one spring will be expanding. Okay. So this results in the controlling torque whose magnitude is directly proportional to the angle of deflection. So the torque tau will be directly proportional to the angle of reflection theta. That is, angle of reflection is nothing but from 0 point to your control value, which is nothing but your theta. Okay. So TD or the tau D is directly proportional to the current I, and so TD is nothing but your deflecting torque. So we have to consider with respect to your TC. So TD is your deflecting torque. TC is directly proportional to the deflecting angle. Okay. So your TD will be directly proportional to the current I at the initial stage. Okay. So at the final stage, coming to the final stage, what happens after the end of your TD or the deflection torque? What happens is that both your controlling torque and the deflection torque will be same. Okay, and due to this property only, you will be having your scale as a linear scale. Okay, in some instruments like wattmeter, the scale won't be linear. Okay, there the process is entirely different. Okay, wherever linear scale is applicable, there you can see these kind of spring control methods. Okay. So moving to the gravity control. So in the gravity control, as the name suggests, the major part is played by your gravity. Okay. So in the gravity control method, a small weight is attached to the spindle of the moving system. So small weight will be attached. So here you can see uh, this is your spindle. Okay. So here they have given you the top view. Here what you can see is that this is your control weight. So here you had balanced weight, right? So similar to the balanced weight, here you will be having a control weight. Okay, due to the gravitational pull. Okay, due to the gravitational pull, a control torque acting in opposite direction of the deflecting torque is produced. So a control torque will be produced over this control weight. Okay. So in this case, over here, the TD is directly proportional to the current. Again, the same criteria what you have seen in the previous condition, but here the TC is directly proportional to your sine of your theta. So in the previous case, what you have seen, that we didn't take into account any kind of a gravity force. But here, we'll taking the gravity force, uh, you have to find the resultant of the torque by using your vertical and your horizontal component. So here you can see clearly. So here this is your what you can say horizontal component, and this is your vertical component. So when you are finding the resultant, you will be taking the combination of these two values. Okay, so with respect to this, your control torque will be always directly proportional to the sine of your angle of deflection. Okay, and this is the main reason your scale is non-linear. As I said, right? So in case of your wattmeter and all, the scale will be non-linear. So such kind of non-linearity scale instruments will be making use of this gravity control method. So moving to the final torque, damping torque. So the damping torque minimizes the oscillation of the pointer. So again coming to the pointer scale. So this is the A position. This is the B position. This is the C position. So the pointer has to travel from A to C. The initial condition will be starting from here. So after some time it will be coming to B. So after at the end it will be coming to C. So C is the final point. Okay. So in absence of this torque, when if this torque is not present, what happens? The pointer continues to oscillate. It moves from A to D and D to A. Okay, such kind of oscillation is possible. So depending on the magnitude of the damping, it can be classified as underdamped, overdamped, and critically damped. So damping methods. First one is your air friction damping. Okay, with the help of your air, friction will be generated and damping occurs. The second one is basically by your eddy current damping. So in case of your current transformer and potential transformer, this is applicable. So coming to your air friction damping, what happens is that a light aluminum frame will be attached to the moving system. So a light aluminum frame, okay. This piston, so this air friction damping is more or less you can find in your speedometers. Okay, your speedometers in your the vehicles will be making use of this kind of air friction damping. So a light aluminum frame will be attached to the moving system. This piston moves. So here you can see the piston. Okay, so this is the chamber. So this piston will be moving in your air chamber closer to onion. At the time of oscillation of the moving system or the pointer, what happens is that the piston will be moving into the chamber. Okay, at that time when it moves into the chamber, the air will be gets compressed because there will be presence of air already in the chamber. So when it's coming out, the air will be flowing inside and the air will be compressed over here. Okay, and if it is compressed means there will be formation of a very high pressure, right? So very high pressure will be formed, and this pressure will be opposing the motion of the piston. Okay, will be opposing the motion of the piston, and therefore the moving system also it gets opposed by this pressure developed in the air chamber. So similarly, if the piston is moving out of the chamber, so in case of this motion, so this is in case of this motion. Okay, so in case of outward motion, so what happens is that the pressure in the closed chamber falls and becomes less than the air pressure. There will be a drop in the pressure. Okay, the pressure difference. Okay, drop in pressure. So motion is thus again will be opposed and oscillations will be damped after the moving. Okay, so coming to the final damping method, this is nothing but a eddy current method. So you know how the eddy currents are produced. We have already seen with respect to your transformer. So here what happens is that this is the arrangement. So here will be your damping magnet. So this is your damping magnet, and this is a spin pointer and spindle. So it's parallel to here, there will be the calibrated scale. Okay, so you can see this in your energy meters and all. Okay, what happens is that there will be a permanent magnet. Okay, this permanent magnet will be inducing your EMF. How we'll be seeing more or less similar to that of the operation of your transformer. So an aluminum frame or damping disc will be mounted on the spindle. So here it is very clear. and free to rotate in the magnetic field. So at the figure C, you can see the rotation of your spin disk. Okay, rotation of your disk. So provided by the damping magnets. Since this disk is rotating with spindle, an EMF will be induced. As I said, whenever there's a current when the current carrying conductor is cut by your uh, cuts your magnetic field, there will be an EMF induced in this. That's what your Faraday's laws of electromagnetic induction. So it clearly gets aligned with your Faraday's laws of electromagnetic induction. So since the disk is a closed circuit, so it is in a closed circuit, the eddy current in the form of concentric circles. So here you can see concentric circle. Okay, concentric circle will be induced in the damping disk. So interaction between this eddy current and the magnetic field, it develops a force on the damping disk. This is the force which opposes the movement of the sheet or the pointer. Okay, so this is what with respect to the three important talks which you have to consider as an essential requirement for your uh, instruments. Okay, measuring instruments. Okay, thank you.